and one Journal-First paper. And as you can see, the first paper is joint work of Nicolas, Behr, and Russ and Russ.
Thank you very much. Yeah, so this is a blue skies paper, so there are no particular specific results. It's more a project. The paper is quite short and easy to read. It's more in a philosophical mode than a technical. So I will try to avoid repeating too much of that, just to give a bit more context for the project. This is joint work with Nick, but I mean, there's a whole load of other people that are involved officially on the project and hopefully beyond that as well. Really. This way. Let's stop working. It's fine. And there we go. Okay. Okay. So the first context is that we recently had a French research agency project which was funded, which is called Carryout. It stands for COG Rewriting for Executable Applied Category Theory. The idea of this project is that we're bringing together a team of people who are expert in proof assistance. In our case, it's, I think, principally COG, but there's nothing that we would like to avoid being COG-centric. Nothing we do should depend on that. So if people want to use Isabel in this context, why not? And we brought together a group also of people who are interested in diagrammatic reasoning, either from a theoretical point of view or from the fact of using it. So Nick and I, we've done a number of quite complicated proofs in the field of graph transformation, which make extensive use of diagrammatic reasoning. So we've got these kind of three groups of people: the users, the theory guys, and the form guys. And the idea was to try and bring these together, make an effort towards the formalization, by which I mean in COG or other systems, of diagrammatic reasoning. And this is something which at the current time may be a surprise for those of you that don't know this field, but it really just doesn't work at this time. So languages like COG, if you remember what Dan Geeker was saying yesterday, the difference between a linear and a one-dimensional word-based syntax, and then moving to more two-dimensional string diagrams or higher dimensional. Something a bit similar going on here. When you have a diagrammatic reasoning, you have immediately a multi-dimensional input. I mean, a square is already 2 dimensions, and very quickly we find ourselves with cubes and hypercubes. Okay? And languages like COG are an extremely linear input, so you have to do a huge amount of serialization just to get started, and it makes everything really completely infeasible. So really, we need to find new ways of doing that. So that's the job of the COG guys, essentially. Then we need some kind of library of basic lemata. So that clearly is dependent on the field in question. So we chose the use case of graph transformation just because it's something that we know about. Okay. So in our case, the library of lemata is things about backs, push-outs, how they interact. And then it's also going to involve formalizing certain of the axiomatic categorical settings, like adhesive categories, which then give you a whole additional battery of basic lemata. So you can think of these as the little building blocks for building larger diagrammatic groups. That's the first aspect of the project. Now, I will come back to these things in a bit more detail after. The second point is that we also are interested in building a system which doesn't just help you write down after the fact, that once you've written your 10 pages on paper, that you can then formalize it in COG. Okay, that's nice because it gives you certainty that your proof is correct or is not, you didn't miss any cases or whatever. Okay. But what we'd really like is to build a system where, in some way, and to some extent, to what extent remains to be seen, but to some extent, we can actually make a collaborative proof effort between the machine and the user. Okay. The idea here is that when you do diagrammatic reasoning, when you're proving things like the concurrency theorem or the local Church-Rosser theorems, these things rapidly diagrams are starting to get very complicated. They're multidimensional. If you can see what to do next, it's usually pretty obvious what to do next. But sometimes if you don't draw the diagram in the right way, but the right way is very dependent on you, right? People see these things differently, they visualize them differently. If you can't see what to do next, then you're completely lost. You've got dozens of objects, there are arrows in all directions, and you don't see what to do. And sometimes a proof seems impossible, where in fact it's just that you haven't drawn the picture in a way that suits you. So the machine there can be a big help because it doesn't have this visualization problem. It can simply detect, oh yeah, here you can apply this lem, or here you can apply this universal property, or so on. And it can just provide suggestions in the first, that's like the first level, right? You can say these are all the things that you could do. Or perhaps more interestingly, it could provide means, and this is out of my field of expertise, but it could say in other proofs that look a bit like this, these are the kinds of steps that we used. I don't know exactly, but that's to be seen. In any case, what would be very useful would be to have a library of reasoning steps which can be searched and used to investigate a current situation. And that would clearly be linked back to the library of Lamach. That would be kind of the foundation of that thing. Now that's obviously a big project. There's a lot to be done there. It's not clear how much you can get done in the time allotted for the project. But it's always nice to have lots of milestones that provide you with at least some concrete advance. But the most obvious one here is to build already a library. This would be in our case in Coq, but as I say, there's no reason for it to be in Coq. It's just because those are the people that we know that's their language. Would be, I think, and this is a little bit off the side of the project itself, because scientifically it's not a particularly complicated problem, but technologically it's a bit more so. The means to connect a text written in LaTeX or some kind of close approximation to that, which would enable you to connect a mathematical text, just a scientific paper or a lecture notes or a monograph, okay, to a formalization. But the first, this would provide the reader with a bit more confidence that in this complicated proofs, they know that this is really done. We see a lot of POPL papers now with a kind of a green tick in the front page saying that it's been very formally verified in something, okay? So there's a similar idea for that, but it would be at the granularity of individual lemmas or theorems rather than the level of a paper. Okay? And then, obviously, if you have the means to build such a system, it would be nice to build a particular one. So in our case, why not do it for the use case in question? Okay? The graph transformation. Plus, we have quite a lot of source material which could, in principle, of course, there are questions of copyright and so on, but there's a lot of material out there that could possibly be reused and then connected back to the library of formalization. So, in a little bit more detail, the idea of this having such a kind of a text, from my point of view, as I said, scientifically, it's a pretty straightforward idea. The idea of a distributed and collaborative resource, that's basically the idea of a wiki. It's been around for several decades. It does, and it's worth remembering, has certain advantages. It gives you the potential to really cover an entire field, because some people will produce something here, others over here. You don't need a team of experts that have to do everything all by themselves. So you lose that particular limitation of the traditional research monograph, which is written by one or a small number of people. And you also, as we know very well, it solves to a very large extent the problem of maintenance of such a thing, correcting the little errors that inevitably sneak in and which could be detected more easily once you have this formalization that is put into place gradually. But also of keeping it up to date as new results come in, just be able to modify text online, and it would remain a single resource for the community, a point of entry in some sense. So as I said, if you have the possibility of linking an informal proof, no, we're not suggesting that you read a text where the proofs are written in Coq, don't you know, something like that. But you could have informal proofs which perhaps could be partially generated from the Coq thing. Okay, that would increases your confidence in what you're reading, or increases it in principle to 100%. But I think also it provides entry points into a literature which has been around now. It's about 50 years since the field of graphic transformation first appeared. And for a young researcher or a newcomer, I myself came to the field as already an established researcher in other fields. And it took me quite some time to situate myself and find, okay, this is the particular kind of graph rewriting I need for my problem. It didn't happen immediately. If there had been some kind of entry point like that, it could have been quite helpful for me. And certainly for young students who just start, to have a basic resource like that, which is up to date, would be, I think, a fantastic thing. So concretely, yeah, we're talking about some kind of presumably online text with a LaTeX appearance to it. I mean, it would be built on LaTeX, obviously, but maybe not written exactly in that way. Again, in wiki style, you have cross-linking and all that kind of stuff within the text. That's the thing. Then the idea would be linked with some sort of markup. Details don't matter really, but to a proper formalization. So the hope there is that you could open up a few things, some of them trivial, some of them a bit less. So on the trivial end of things, you could have, you know, a green tick after a lemma. Or you could have the ability just by, you know, hovering with your mouse or by tapping, you get a little pop-up to visualize what the formalization looks like. If you want to know, okay, what is this definition? How does it actually look in Coq? Well, you can just click it and it will just pop up and you'll be able to see it. Incidentally, could be a way to learn Coq for people like me that are just very kind of white belt in that kind of field. On the slightly less trivial level, when you have a bunch of results in a Coq file, you can perform some quite interesting analyses that tell you how different results depend on each other. So this could provide a means to perhaps organize the presentation in a way that's well, perhaps it would help you to organize presentation in a way that is more ergonomic, cognitively ergonomic. Okay, so you have the basic stuff, and you can see how things fit together, and also to suggest that a given result, although it was proved in this way, it could actually be proved using weaker assumptions in a different way. This is something which, yes, you can spend hours in thinking about this, trying to fiddle, but with this kind of thing in Coq, dependency graphic, I believe they call it, this might simplify and accelerate that kind of process. When you've got a lot of results, which we do in this field, that could be also helpful. And again, obviously, there's questions about how to use all the bibliographic stuff which exists now with the DOIs. That would obviously need to be integrated, but that's more on the sort of more trivial end of the scale. That was kind of a higher level description. The project is just getting underway. The first steps are being taken. So in fact, we cheated a bit, started in advance. So I had last year a student in his final year of masters who started working on the formalization of a library of basic results. Excuse me. So the guy's called Samuel, and he was working on Koch formalization of a number of the basic notions required for categorical reasoning, okay, and specific to graph transformation, because otherwise it's too much to do. So he was formalizing things like limits, co-limits, and particular special cases like wax, shells, things like that. Also, some of the more exotic operations, such as final pullback complements, which is sort of limits and co-limits at the same time, one neither. And then also some of the more exotic things like the multi-limits, multi-co-limits that it turns out in the work I've been doing with Nick provide useful structures to unify otherwise a bunch of ideas. Okay? So these things are clearly related to limits and co-limits, but their formalization is a lot more subtle. That took quite a lot of time to figure out how to do that in a good way. But we believe that in the end we got to a nice way of doing that. And this was work that we did with Damien Pousse, who's a guy who works in the same lab as me and who's really a specialist in Koch. He doesn't know anything much about graph transformation, so it was quite a complementary effort. Now, this work by necessity used the first decent Koch library for category theory that we could find. So there's a guy called John Wheatley who some years ago developed quite a large, extensive library. So everything that we did was based on that, with a few little modifications in some places where some of his design choices were unhelpful for the way that we were trying to work. Okay. But to a very, very large extent, it was based on that. And if you're interested to see the concrete output, he wrote a short report for his master's defense, and all of the Koch is available on his GitLab account. In the context of the project, the Carryout project itself, first steps are being taken by a group in Sofia, so in the south of France, just by Nice, led by Cyril Cohen, who's a researcher there, aided by a postdoc who just recruited, Paolo. And then Reiko, who also works as a permanent position also with Cyril. So in that lab, over the last few years, they've been building kind of, I don't know what they call it exactly, extension to Koch, which they call hierarchy builder. So this is a way, when you're doing formalization, that you can build things up little piece by little piece in a sort of style of inheritance. Okay? So this was done initially in the context of a project called MathComp, where they're trying to formalize large parts of traditional mathematics. So this has nothing to do with diagrammatic reasoning. But typically, they could say, okay, this is how you formalize a monoid. Then this is how you formalize the fact that it's commutative, or the fact that it has this or that. And you can simply take the pieces that you're interested in to build. So if you have a monoid and it's commutative, and then you can also invert elements, then you can combine those things to get a commutative group, for example. If you only want the group, then you ignore the commutativity part. It's a kind of a plug and play way of quickly generating Koch formalizations in a hierarchical manner with inheritance, so that you don't have to redo everything every time. If you want to define a group, you don't have to start from scratch. You can start with the pieces that you already have and just plug together the things that you need. So Cyril wanted to apply the same ideas, but rather than for algebra, to do it for category theory. So this is an effort which is now underway. Yeah, okay. So this is something that's underway. He presented a first part of that at the kickoff meeting of a few months ago. And Samuel, who did his master's last year, he's now completed, he graduated, and he will be starting his PhD in Lyon with myself and Damien, that I already mentioned, in September. So the very first thing that he'll be doing is to start from what he did last year and basically to refactor that via the new developments of Cyril and Polo. The aim being that we hope, first of all, to provide feedback to the group developing the hierarchy builder version of category theory, but to test what they're doing and also to provide some kind of priority as to what they should do next, okay? Because it's obviously a vast effort. This would also give us a good solid foundation for the rest, okay? But then the next step, which is something that he started, I didn't mention.
Yes. What is the present relation with the hierarchy builder and the cock, the basic cock? So it is in cock. It's an extension.
Yes, cock is an extension. So it's something that sits a little bit above cock. It enables you to build these theories in this kind of inheritance way. And behind the scenes, it will generate for you the
so it's an addition of the cock.
Yes.
The idea is to move the formalization of category theory as a dog cock to a more structured one.
Exactly.
Exploiting the hierarchy.
Exactly. Yeah.
This requires.
This seems to require a great deal of work. Yes. Yes.
The way I understood it from a IRIF specification point of view is that essentially the structure layer gives you extensions, unions, parameterizations of specifications. So basically, like this kind of.
Which means that the big library category theory doesn't have this feature.
No.
Right. Therefore, it's much more difficult to. Thanks for the.
It's not so much that you couldn't work with it. It's not so scalable. Plus, my understanding of the weekly library is that it's no longer being actively maintained. It's there and it works, but
I can maybe comment on this.
Yes.
So John's working on it. My co-worker.
he is working with it still.
From time to time.
Okay.
He's very interested to hear the interactions. I'm not sure if you have context.
No, Samuel ever actually contacted him, but in that case,
He's very supportive. Or just reach out or let me know and I will.
okay. Well, thank you. We should do that then. Okay. But it didn't seem to have been modified recently when we were looking at it. But yeah, if he's doing it from time to time, sure. Okay. But that would be nice. My slides are quite dense. What were those? It's here. Yeah. Okay. There's something which I didn't mention in what Samuel did last year because it was really just very preliminary. Was that clearly when we in the field of graph transformation, we make use of a great number of different axiomatic category theories, right? This could be Topoi or quasi-Topoi, adhesive categories, and many variants of those. And in fact, it's a slightly different level. These different, these sort of families of axioms could also benefit from a hierarchy builder's style of presentation. You know, between an adhesive category and an RM quasi-adhesive category, there's a great deal which is in common, and there's a small amount which is different. So one could again formalize these things as little plug and play pieces, and then use that to formulate formally these different theories here. So that would be a second step for Samuel, and then it would be a question of how to best make use of that, how to connect it back to what I was saying. So to come back to this part here, okay? The library of reasoning steps. Basically, when you're in a quasi-Topos, you have one battery of reasoning steps that's available to you. If you're in an adhesive category, you have a different battery. There's clearly a great deal of overlap, which is where the hierarchy building comes in. But we'll need to find ways of making that ergonomic. I think that might actually be quite difficult, but let's be on being within this. And in any case, and then clearly the real aim of all this is not just to build little bits and pieces of lemmas and so on, but to really to have serious proofs. So the concurrency theorem, or confluence theorems, these kinds of things. And to have this for various axiomatic settings, but hopefully in a way which shares as much as possible. Right, that was kind of the point I was saying just a moment ago. Those parts of the proof which are common to two axiomatic systems shouldn't be duplicated in principle. And of course, then, as well as the different axiomatic settings, there are all the various different rewriting semantics and settings that you can consider. What kind of rules do you want? Are they linear? Or are they allowed to be non-linear, or at least on one side or the other? And then are you interested in DPO, SESQI, or in PBPO, or in PBPO plus, etc., etc. Okay. And as Nick and I have discovered, sometimes, and I think everybody else knows as well, making a slightly different choice of the kind of rules, or the exact semantics, or the exact setting, all of a sudden, things that seem to be obvious in one case just break in another. So it'd be nice to have, once and for all, a kind of a formalized setting where we can really understand in a plug and play fashion which combinations work and which ones, particularly which ones don't. Okay. All of that's the stuff which is underway or will very soon be underway. The more interesting thing is what can come next, and this loops back to the point of using the system not just to write down transcripts and proofs, but to actually develop them. So for this, there are several pieces that would be required. So some kind of formal calculus of diagrammatic reasoning steps. So this would view a diagram as a graph. Seems like a rather natural idea. And to represent a step of reasoning, so as I said, give you an example of the existence of the universal arrow, there are many others, right? That could actually be seen as a rewrite of that graph. Now that's slightly a coincidence that's actually a rewriting step.
The time left, if you could kind of wrap up, so we have a few questions.
Yeah. This is the last slide.
Thank you.
Yeah. So we are planning to look again in the autumn with a group of category theorists in Paris, theories of sketches and generalized sketches. This might be a good basis for this stuff. Then, as I was saying before, to have a searchable and extensible database of these steps. It's not worth saying too much more about that, but that's part of the project anyway. And the thing which is really more speculative, but I think is perhaps the most interesting, is how to integrate these ideas with the proof assistant itself. But way back, they had a notion of proof by pointing, which is a way of for the human to guide the proof assistant by saying, metaphorically by pointing, this is where you need to work next. You know, it's clearly when we do diagrams, proofs on a blackboard between two people, we're always pointing and tracing out squares and so on. But a way of generalizing that in an ergonomic fashion, the proof system would be extremely interesting. I'll stop there.
Okay, thank you.
Thank you.
Questions, comments?
Als book kind of proof language like these are, it's quite readable piece about.
Really, no. Yeah, the only code that I've seen is a pretty low level. I mean, it's natural, but it's not very human readable.
Okay.
It's really.
It seems also quite nice to have for like thinking.
Mm-hmm. I mean, that could be.
No, people are working on it, perhaps.
Not to my knowledge. Okay. Not to my knowledge, but.
There was some accounting test.
Okay.
Maybe to comment that our vision is that many of our proofs are actually based on pure computative diagram reasoning. And I mean, we would much prefer to basically use this as an elementary piece of proof so that you can read the proof as visually as you would read it if you were to serialize it. So that's the real goal of the project, find a way of actually integrating something like a diagram editor with a way of
assigning a change in the diagram to certain reasoning of this. Yeah. And if there's maybe a chance to formalize this in such a way that you do not need to write code. So I think that would basically, but I mean, of course, that's the vision.
Yeah, that's
I mean, with the diagram, you go a long way in this field, so.
Reiko?
Yeah, just I don't know, maybe it's a longer discussion, but I think as a related and less technically demanding project, which would be to set up a wiki for graph writing for generally, which doesn't need to go down to formalizations and proofs, but sort of stay at the conceptual level, introduce the sort of language feature essentially that you have, and which could link and also introduce the kind of general concepts of the theory, and then link to these more deeply sort of proof theoretic.
I mean, I actually have a related comment. I mean, as far as a monograph is concerned, it's called a monograph of graph transformation. In my view, at least, graph transformation is more than just category theory. There's, there are constructions. There is stuff like benchmarking, or people may say, I have a new matching algorithm here. So here, I would find it nice as all of this somehow would be in that space.
Question of scope here.
Yes.
Rather than this, the scope here is really of the categorical theory. But
My point was, it's called living monograph of graph transformation, not of categories.
So I could say that the format we are developing will particularly have a good collaboration. Like this, it'll be essentially like writing large monograph. So nothing prevents having applied articles in there. The one thing you want is that if the moment you start drawing diagrams, is in the back end, there will be already like the COG formalization linked to that.
No, I fully agree with all of what you said. I'm just saying, let's be inclusive and all this stuff somehow.
I mean, we plan actually next year, if we are far enough with the development of the platform, really test it out, and I mean, already reach out to some of the community, because we think, in the end of the day, for the technology nowadays, it's very easy to have something like living monographs set up. Essentially be writing a large LaTeX document, so we can certainly experiment.
Any other quick question? Yeah.
Well, to touch on to that, when you are there and when you are looking for people who then try this out and help you with it,
certainly.
Become a member and be able to see.
Yeah, we should say we have a mailing list on. We have a
Should have
web
put
page.
that on the slide, actually.
Can you link it to the program? Then we can. The web page. We have a web page for this. So
okay.
And we have a mailing list.
There is a mailing list already. Yeah, I can. Yeah, I should upload that.
So
you can upload your slides to the conference management system. There's instructions around that. Maybe if you put the contact details on there.
But what I can do is
the slides there, and we can just click on the slides.
Yeah, I will update. I'll put a final slide there. That would be easier than mucking around on the web page. Knowing me, I'll probably mess it up. Yeah, so just to come back to what you were saying, absolutely. I'd rather they're focused.
No, that's fine. I'm just trying to point out there's other stuff. It would be nice if we somehow link the whole things together.
Yeah, I mean, really, I think if there could be a single community resource, it would be really fantastic. Be really a great thing.
Even stuff like graph drawing. I mean, it's an own community.
Exactly.
It's relevant for us, right?
Yeah. And in fact, what we really like to happen is that at the end of the day, if somebody puts an applied topic, and then somebody from our theory field would say, okay, we need this and that category, so we link it in. But I mean, that would be the ideal outcome. But I mean, we need to experiment. What shows it shows.
And a way to bring together all of the tool developments that take place in the community, so that they don't just be attached to one single paper and then sort of wither. To have some sort of centralized repository, at least possibly integration. Well, that's a different project. Okay, but yeah.
Okay. There are no other urgent questions. Then I think we stop here with this program. Okay. Next paper is actually a local paper by Adam Machowczyk and Reiko is presenting.
Right.
Sorry to.
I should know how to do that. Need to find the. Start automatically. Loading atoms. I'm the first one using PowerPoint on this one.
That's so.
Okay. Yeah. Yes, your screen sharing.
There's no green border around this window, so I think it's sharing the whole window stuff.
Yeah, all right.
Stop sharing in the beginning of the screen.
Okay. Right, what am I sharing? Oh, that's good. I'm sharing the presenter screen, I think, now. Yeah, so that is not what we want. So I need to see how to flip these. What's that one?
Yeah, share this one, right?
Okay.
Screen 2.
It's a green box. Moderately confident. Okay, good. Let's see if that works.
Worked before. Try again.
Hey, okay, cool. Glad for that. Writing should be big enough. Right, yeah. So thank you. So this is pretty much a new idea that's appropriate for this kind of talk. It also means that it's essentially one example, slightly extended example, a few pointers to what one could do next, and some sort of general philosophy behind it, but not really any deep results at the moment. So my favorite slide, just to say we have lots of different uses of graph, as I don't have to tell you. And not surprisingly, that led to development of machine learning techniques for graphs. Graph neural networks are one of them that kind of became popular in the last few years. Maybe the first papers are by now maybe 7-8 years ago, but they really went off maybe about 3 years ago with substantial applications. And the idea is you basically have a neural network that operates on a graph, and you can essentially learn or infer information from the graph. So if you think that the graph has so some nodes of the graph are labeled with certain properties, let's say, but not all of them, then the neural network would be able to infer those features also for the nodes that are not labeled. So that's node attributes. So if there are edges between certain nodes in the graph, you could generalize basically to other cases where those edges do not exist. And so you can infer nodes, edges, graph properties more generally, so even global graph properties in principle. And there are lots of different applications. So I think one that was particularly impressive was which you probably heard about, was that they managed to compute geometries of so basically the plotting folding problems, and these are basically impossible to solve algorithmically, or almost impossible to solve algorithmically, but they basically managed to do that using a graph neural network, which opens up huge applications in drug discovery, for example. So that was, I think, 2 years ago. That was a sort of major breakthrough. Anyway, so that's graph neural networks. Graph rewriting, of course, is rule-based manipulation of graphs, and all the things that I described are basically graph manipulation. So if adding nodes, adding edges, manipulating attributes. So it's natural to say
principle that graph neural networks are the form of graph rewriting, or I mean, certainly graph transformation, in the sense that the graph is manipulated in some way. Obviously, they don't necessarily describe that in a rule-based way. Yeah, but one could, yeah, because obviously it's everything that we do on the graph we can describe in a rule-based way. So that's the idea. So the hypothesis essentially is that graph rewriting subsumes graph neural network in a computational sense. And so I could use that as a model to look at different variants and to study structures and algorithms and so on. We could also take sort of specific graph neural networks and like re-implement them or model them as graph rewriting systems. Yeah, so that's the starting point for us here. And because it's always good to come up with a new name, we thought of these, called this graph rewriting networks. We have in background. Okay. So what I'm going to do now is I'm going through an example where we basically experimented with to explain the ideas, and you see at the same time, at least in principle, how a graph neural network might work. Even as I said, this is our own tape. This is the kind of graph rewriting version of it, but you see the kind of concepts and mechanisms there. And at the same time, introducing the rule-based version of it. Yeah. So a simple example, which is quite typical actually for this domain, is the recommender system. Okay, so recommending social media posts, let's say, but I also use this to recommend products. You buy products of Amazon, it tells you someone who bought this also bought the other thing. So that's basically also a graph neural network in the background there. So the idea is that we have users, we have posts that they can make, and they can make, users can engage with posts, yeah, so they can, like them or forward them or reply to them, things like that. And we have different levels of engagement. So maybe a like is less than a retweet, for example. We have a number of attributes apart from that are a little bit more related to the actual mechanism of the graph neural networks. So ops basically tells us whether the engagement here is actually one that we have observed, that is data that we actually get from the let's say database of the social network, or if it's something that was predicted or inferred. Yeah, because that's important, because we want to learn from the ones that are observed, but not from the ones that we inferred ourselves. There is something about errors, because we need to sort of calculate errors for training. And there's kind of technical thing here, counting, because I couldn't find a way in which to figure out the cardinality of a multi-object or set object in Groove. So I basically added a counter attribute there, but you can maybe press bar later on. And yeah, equally for posts, the weights associated with posts that tell us how good is this post in representing other posts by this user. So is this the kind of average post that this user makes, or is it very different? Because also that's important for the prediction, and then obviously users. And there's an update attribute here, because one of the things that we want to do is incremental updates, dynamic incremental updates. Yeah, which sort of falls slightly out of the kind of normal scope of what graph neural networks would do, because typically they're not incremental. Okay, so for that, a couple of rules. So this is not the graph neural network mechanism. This is really just the rules that sort of simulate the dynamic evolution of the data. Yeah, so we can have new users, we can have existing users making new posts, and we can have users engaging with existing posts by other users. So this is a user which has made a post, and this is another user who engages with that post. Yeah, and here we see, just for testing purposes, I think we just have 3 different variants of this with different levels of engagement. But that's just normally you would have some kind of input parameter there for the level of engagement, but we just want to keep it simple. Yeah, as I said, the update attribute on the user is true if it's a new user or the author of a new engagement, because that means that, or of a new post with a new engagement, because that means that we may need to do some retraining on that one. So that's the kind of underlying dynamics. And then it gets a bit more interesting because now we're encoding the inference rules for a graph neural network. And so what you can see here took quite a while to get right. So essentially what we want to do is we say, as if we have a user and a post, okay, we want to predict the engagement of that user with that post. Okay, we create a new engagement node. Yeah, so the fact that this is sort of shaded green and red means it's basically the combination of a negative application condition and the creation of a new node. So create a new node if there isn't already one. Okay. So we initialize that saying this is not observed, but third, and then there's a kind of long formula here, which essentially says that we take the average over all the other engagements of this user with posts by that user. Yeah, and that is the predicted engagement of that particular user. Okay, so that's the idea. And now you see all of those little quantifiers here. So this one here basically gives us the quantification that I just mentioned. Yeah, so this basically says that it's not just one engagement and one post and one user, but these are all the engagements and posts of that user with that with posts by the other user. So it's a universally quantified pattern. Okay, so that's that's the inner level of the quantification. The outer level of the quantification does that. We don't just do that for one pair of user and post, but we do that for all pairs of users and posts in the graph at the same time. Yeah, so that basically one level says all pairs of users and posts in the graph. Okay, and then for each of them, we look at all paths of engagement, post, and user. And take the average, as I said, over those and add that as a weighted sum to as a strength attribute for that. Yeah, so the inner quantification is necessary because we want to take the average over all those paths. The outer quantification is necessary because we don't want to write a loop that goes through all the pairs of nodes sort of sequentially in the graph, which we could do. So there's nothing technically wrong with that. Yeah, but it's easier to control if we do it for everything simultaneously. So it's basically a maximum parallel application of the other route. But that's why you have these two levels of nesting. Yeah, so that's and because Groove is good at that kind of thing, I found it easier to do it that way than to basically write a loop and control that and so on. Okay, and this is just the same formula which I just. Okay, but this is the usual structure. So we always have these two level nested, universally quantified. Okay, so that's the inference part, but that inference part is based on, as part of the formula, we use the weight of the post because it's basically a weighted average, weighted by how representative the posts are that we've seen before. Yeah, so we basically take some posts more seriously because they are more representative of that user than others. Okay, so So we still need to train those weights. Okay, and in order to do that, the typical method in neural network is what is called a back propagation rule, and in particular here it's called a gradient descent rule or delta rule. So the idea is that you calculate an error, and then the error basically tells you where and how much you need to adjust the weights in order to reduce that error. Yeah? So the first step is you calculate the error, and the error is essentially the difference between the actual strength that you observed. So this is an observed engagement. Yeah. So you have an actual strength there that was observed. Okay. But then you can also think of this as an engagement maybe that you may be able to predict. So you're trying to predict it. You see what strengths, what predicted strengths you get, and then you take the difference between the two. So that's basically the error of your prediction for the case that you actually have the ground truth. Okay? So that's the error per engagement, and then you add up all the errors of all the engagements. Yeah? And then you get a kind of a global error, which is why we have this error here, where you keep track of that. And then we need to control that in the sense that we need to make sure that so it's clear in principle one can prove that in general for this data rule that I mean it's not something that we done, but in general in neural networks that the error always goes down if you do that, yeah, because you adjust the weights in such a way that the error is reduced. But you obviously want to stop somewhere, so you basically stop when the difference between the error in one inference in one training step and the next training step falls below a certain threshold. Yeah, so if the error doesn't decrease anymore, or not significantly, then you say, okay, now I'm done. So that's why you need the delta, which is basically the difference between the current error and the previous error. Yeah. Then it's basically an updating condition here, which says if the error, you only continue with this if the error is still above the threshold, and otherwise you stop. So that's the error rule, and then you have the actual gradient descent rule, which uses the error in order to update the weights. Yeah? So you take the error of the engagement, and then now you're looking at it from the point of view of the post. So you say you take the error of all the average error of all the engagements that this post, the weight in the post had helped to calculate. Yeah, and then multiply that with the actual current weight of that post. Yeah, and then you get a new weight here, which then, as I said, is in general for this data rule, you can show that it's leading to a smaller error in the next iteration. So
it always goes on. Or can some somehow be negative?
Good question. Where something negative? Yes, it can. No, the error can be negative because the error obviously is a difference. So the error can be. Yeah, I mean, if the error is negative, something. But you see the same kind of nested structure, only that in this case, the top level quantification is over all the posts, because you need to adjust the post, and then the next level where you basically the weighted sum is over the engagements. Yeah, but this is the kind of typical pattern. Right. So we need to control this. So even if there is already quite a lot of control, there's a sort of simple control program here. And we have one part, this just represents the training, just the function of the training. There's not much of a instruction here. So training, there's one for inference. So the error rule and the delta rule are only applied once, because one application of each of those rules basically processes the entire graph. Yeah? So that's why we don't have to program any loops here. The error rule explicitly controls this for as long as possible thing, because if the error rule isn't applicable anymore, because the error falls below, or the delta falls below the threshold, then this sequence isn't applicable anymore, and then we stop. So that's basically, so the training is not just sort of one iteration. Here is a number of iterations until the error falls below the delta falls below the threshold, and then that. And then we have the update. And the update is just, I mean, this is just a test case, basically. Yeah? It says, okay, so let's see what happens if you create one new user, one new post, and 2 new engagements, and then we do it all over again and see how this goes. Yeah, so this is essentially simulating the dynamic changes in the data in the real world. Obviously, we don't have the link to the real world. We have to do it ourselves. In reality, you could think of this as an API that accesses the real data.
But is this actual groove code that you're using here?
Yeah. This is the control program. Yeah, okay. And then this is the actual sort of main program. So we do training, inference once, then we update, and then we do training and inference again. So just as a kind of test scenario. Okay, and then just to show you a simple example in actual application. So that's a simple graph here: 3 users, 3 posts, 6 engagements, some observed, and some they're all okay.
Suddenly we have a new code also.
Yeah, that is.
Yeah, we can all see where it comes from.
In spirit, Gabi is always good. So yeah, so that's the start graph, and then the first thing we do is the training. So as you remember, so this is the same after the first training cycle. So you can see the error node here, which is kind of control node for the training. You see that the error is 0.8. I mean, that's just the sum of all the errors of all the engagements, but you see that the delta is basically below that. I can't remember if it was something 1. I mean, just below, because it's the 9 here, but that's basically the point where we say this is not stabilized. And you see that, so they have the engagements have all the error node, the error values here. So these are the difference between what would have happened if I predicted that with what was actually observed. And you see that the weights of the posts have also been adjusted. I think they're actually all positive.
The error on the top right.
Huh?
The error on the top right now is negative.
Yeah, several errors also on the.
Yeah, okay. So the errors are not all positive, but the weights of the. I was wondering whether the weights could be negative, but yeah, but you're right. Yeah. Okay, so that's the training, and then the final example here is. So again, this is after we've added, as I said, a couple of a new user, a new post, a couple of new engagements, did the training again, because you see all of those sort of funny numbers here. So this is already after the training on the update, on the incremental update. Yeah, and you should see at this stage that all the update values for the users are false, because it's basically done. So update basically means, if an update is true, it basically means something has been updated but not retrained yet. But obviously this is all true now, false now in all those cases. And yeah, we did again change the weights. I don't think there's much more interesting. Yeah.
If on the top one there's engagement with an observation false, this is the predicted one, or?
Yes, so if the ops is false, that means that's a predicted. That's basically computed as an average, as I said, from the other one. So all the original ones were observed. I think that may be actually the only one which is really predicted here in this example. All the other ones were there before, and the other two were also. Okay, so that's essentially the run through the example. Makes sense? Right, so a bit of a general discussion then.
Yeah, a few minutes because yeah.
So this was not the way in which normally a graph neural network is represented. So it's basically a translation of the ideas of graph neural networks into graph rewriting and a kind of re-implementation of some of the ideas, but essentially ignoring a lot of the restrictions that graph neural networks normally carry, because normally they work on homogeneous graphs, so not typed graphs. All the nodes have the same type, essentially, and the same attributes. Often they are simple graphs and undirected graphs. I mean, not always, there are a few variants there as well. That's actually the second thing I wanted to say. But apart from that, we followed essentially the philosophy. So we use graphs to represent the data and for the inference and training. It's a form of semi-supervised learning in the sense that some parts are labeled. So for some parts, we know what the right answers are because the observed nodes are there, but not necessarily for all cases. So it's basically a combination where the data set is partly labeled and we essentially complete the labeling as in machine learning, where meaning that for the things that are labeled, we know what the right answer should be. Yeah, and we rely heavily on the graph structure, of course. So the closest thing in the literature that you find to this is called message passing neural network, and I maybe not much of a point in explaining all those detailed formulas here, but the idea is essentially that you have you propagate information locally from one node to the next node, or basically one node collects information from all its neighboring nodes, and essentially, I mean, typically takes some kind of average or some kind of aggregation of the data in order to compute its own next state. So this is what is this. There may be two functions here. One is the NT, which is the basically this is the node saying here's all the relevant information that I have that I will send out to all my neighbors. So that's the message in graph neural networks. And then it's the update function where the node basically updates its own values. And in our case, so these are sort of typically sort of weighted sums. And both of these functions are essentially neural networks or implemented by neural networks. I mean, neural network is essentially weighted sum. So that's essentially our equation for strengths, and in this case, the update function is essentially the identity. So what happens here in the update function sometimes is that you have thresholds. So if you want to make a Boolean decision, then obviously you get kind of continuous input values, but then you need to implement a threshold. So but we don't have a threshold here because we have a numerical continuous value. Okay, so that's the idea. So if you compare that, as I said already, typically what happens is we are not, I mean, in our approach, we are not limited to homogeneous graphs, but we can do heterogeneous as well. That means that if you wanted to model the same problem in graph neural networks, in traditional graph neural networks, you would have to encode that in a different way. So you would have one type of node, which would be users. And then all of this chain of one user makes a post and there's engagement with that by another user. So this kind of path over three edges and two nodes would be one edge. So then you get an untyped graph, and the engagement, the strength of the engagement would be an attribute of that edge. So that would be the way in which to sort of graph neural network people normally encode encode that. So in addition to that, we obviously included dynamic updates, because once you have this kind of operational approach that we have, it's relatively easy. The graph neural networks will struggle with that, mainly because they work with this matrix representation, and you cannot really add easily nodes to matrices, because you would change the dimensions of the matrix. Yeah, so it's not impossible, but it makes, I don't think that the standard sort of libraries would support that really well. Right, so that's essentially what I wanted to say. So, so we basically reimagined the graph neural networks without taking much care about sort of efficient implementation of the structures themselves and of the computations on them. Yeah, I mean, it's efficient as much as can say on the graph rewriting side, but obviously with a more efficient representation of graphs if you just want to compute on static graphs. Yeah, and I mean, we like to think of this as a semantic foundation, but also potentially engineering method that one could use, in the sense that one could design the methods in this way, in a more flexible way. And then if we want to map this to a existing sort of efficient graph neural network implementation, is a kind of model transformation or code generation problem in a sense of a model-driven development approach. But we haven't really got to that stage yet. So it's because there's partly because there are lots of different variants of the graph neural networks that one needs to understand first, and to understand what is the actual target. Okay, that's what I wanted to say. Thank you.
Questions? Very clear. Okay, because we're late, I think we leave it.
Okay.
Okay, then our last
sharing or
coming session is by Nicolas. Actually, Journal-First paper, Compositionality of Rewriting Rules with
You know how to operate this, just about. So you're using with the slide? No. You just download it and then basically present it as PDF to you.
It's like a presentation.
That's from the program.
Was collecting everything. Usually I leave everything behind. So that's the regular class. Classes are like, yeah, so yeah. Slides are coming up.
Yes. Oh, I know.
Oh yeah, I forgot to mention that's a co-author, John Krivine.
I don't know if you can tell that I'm a Mac user. Okay, yes, yeah.
Just having told it to open with Adobe Reader, now you go actually open it again.
Yeah. Okay. Here we go.
Now click on.
Okay. Okay.
Well, first need to share this.
Okay, I think it's showing already, right?
Yeah.
Yeah, okay. There we go. Mac user.
Okay. I'll try to start here because I somehow
No.
I would stand. Okay, well, thanks a lot. Also, thanks for the opportunity to give this sort of journal-first track. For me, that's quite nice because I can talk about a paper which, for me, was quite important for a lot of developments in practice with graph transformation of my own work. So, in particular, it's joint work with Krivine. We had a postdoc project, Marie project at IRIF, starting in 2017, and this was the main outcome of this project. But for some reason, I never really gave a talk about it directly because it was published in a category theory or applied category theory journal. It's actually one of the first submissions for that journal. And also in the meantime, in joint work also with Russ, I think we found a better formalization maybe. So, I mean, I'm going to take the opportunity in this talk to exactly present you the contents of that paper, but in a slightly modernized fashion. And main point being, in that paper, we basically analyze under which situations are these traditional calculi of application conditions useful for compositional reasoning model writings. That's, I'll say in a moment what I mean by that. But we also actually introduce the calculus of constraints conditions for set-free push-out semantics. And because the double push-out semantics condition was necessary for organic chemistry in our applications, and the set-free push-out condition was necessary for the biochemistry. So they have it for large-scale applications. And I mean, these slides are already on the program, and I'm just going to give the quick word to saying that once we have this calculus of conditions with compositionality, the advertisement slogan is that you can implement a lot of practically relevant problems. For example, I have a paper where I talk a little bit about what sort of combinatorics you can do with graph writing with conditions. For example, you can reason about trees. And then, I mean, there's famous one in the sense of famous, like large again and long, but I mean, it's about how to compute with biochemistry and organic chemistry and graph writing. So, I mean, I think the main point is that for most realistic applications of graph-like structures, you need to usually implement some constraints on the graphical structures. And our advantage as graph transformation community is then that we know how to still manipulate these objects while respecting constraints. But it has to be done in such a way that for most of these applications, that reasoning steps, sequences are still consistent. And there is a problem. And I mean, that was one of the funniest observations for me because I wasn't really from the graph transformation community initially. And so for me, it was sort of a surprise that people didn't think really about sequence of transformation. So the sort of coup d'etat is already simple graphs. So it's nothing complicated. So here's an implementation of simple graphs by Martin Doing. But I mean, more to the point, it's a simple graph. It's just you have a set of edges, a set of vertices. And the main point is that you cannot link two vertices with more than one edge in one direction. Being witnessed here by that, this is a mono. But that's one implementation. That's a nice category of quasi-compos, as we learned yesterday. And then there's another option, and of course I'll talk more about this later. Well, you could just start from direct multigraphs and implement the global condition, which prevents you from having, sorry, they should be parallel arrows, sorry. So that there must never be two vertices linked with more than one arrow in one direction. So these are two two alternative ways of speaking about simple graphs. And so let's think about what happens when we so we want to reason about sequences of transformations. And I mean, the simplest thing you can do on simple graphs, you can create edges and delete edges. And in this little comic strip, what you see is like just a very simple sequence. We create an edge, we delete an edge, and then we create an edge again. I mean, very mesmerizing stuff. But the problem, if you do not work with one of the previous implementation of simple graph, is just try to do this in multigraphs. Here you would even say, oh, maybe I can reason somehow this will not violate my constraints if I act on two vertices that are not linked. Fine. But the deeper problem is that now in this calculus of applying conditions or of applying rules, you can compose sequences of rule applications. And when you do that, you seem to get two alternative results here. So if you first compose the deletion of an edge with the creation of an edge, well, you get just a keeping of an edge. And that doesn't seem to commute with this operation of creating an edge where you attack exactly the edge that you will then intermittently delete and recreate. So here it's a non-commutative, I mean, non-sequential commutative operation. But if you then look at the other possibility, now you look at the first two steps here. I mean, creating an edge and then deleting it. Afterwards, you're left with just having two vertices that are identically kept. Well, that's certainly sequentially commutative with this operation of creating an edge because you're identically touching just the vertices. So something is clearly going wrong. And the first funny observation is that if you think about simple graphs and you allow arbitrary monic matches, and it so happens to not be a compositional writing theory. So what goes wrong is even like the concurrency theorem goes wrong. So you can get, it's not so much the concurrency theorem, but the associativity theorem. So you're not able to reason, I mean, the causality is no longer sort of modular. I mean, you can no longer reason on the basis of binary comparisons of steps. Now that is very funny because, I mean, that is an essential elementary example. It's very bad because something like simple graph is a starting point for any sort of chemistry theory. So the answer then from this community would be, well, first of all, you cannot really rewrite simple graphs. In brackets, Fabio Garducci and colleagues have just presented last year a paper that this is an n-adhesive category if you allow for the rules arbitrary monics, but then for the matches regular honors. So I mean, there is a way of doing this compositionally. And the trick is essentially saying that, well, so in simple graphs, this here is an impossible match. So in the category where you have regular monos as matches, regular monos are the edge reflecting ones, this simply would never happen. You cannot match like this. There's simply not a, I mean, because it's a non-counter example because it is not a causal sequence of events. And then for the calculus of implementing simple graphs with conditions, you simply would find that if you create an edge, you have to have a condition that says there is not already one here. And then if you combine it with the edge deletion, afterwards you're left with a root which is two identical capabilities, but with the edge condition they are not linked in that direction. So again, I mean, you do not get this counter example. But you see, I mean, it is quite a tricky business. And I mean, this was just simple graphs. We are not even talking yet about these very complicated biochemical data types. And so, I mean, for me, what was tough at the point was that literature on writing with conditions is quite rich because, I mean, the concept originated already, I think, in the 80s, even, and the work of Heckel, I think. And then later, Penniman and Heckel had like a large, I mean, the technology just got lifted to a very compact level. So there's a nice series of papers around 2010, and I think the UG series of Penniman. And so there is in principle this idea, well-developed idea of, for example, if you have to double push-out writing, how do you endow it with conditions? But I mean, then the moment you start looking at compositions of writing steps, concurrency theorem and such, there's quite an intricate technology involved. And the goal of this project was to formalize properly, I mean, at which point do you need which axiom so that we can say, can we do our beloved compositional writing, let's say for biochemistry, where we need some sort of simple type graphs and so on. Okay, and right, and so the main piece where we will test the technology is exactly in the moment we do the concurrency theorem. So I mean, the reasoning about derivation sequences versus reasoning about sort of some sort of composite rules which act in one step. But the whole thing endowed with conditions. That makes it a little bit intricate. Okay, and actually, I think I have to start here. And so the structure of the talk will be: so first I will introduce briefly this calculus of constraints and conditions, the sense of Heckel and Penniman. Then I'll speak about what you need in order to make it compositional, and at the end I'll give a few outlooks to some interesting ongoing problems. Right, so we will need throughout the talk this concept of stable system of monics. So the M and N adhesive will be it's a class of monics which is closed under composition. It's mimicking this property of monomorphisms, that if you have a composition of two morphisms and the second one is in the class and the first one also has to be in the class. And then we want that the category has pullbacks along these morphisms, and that these pullbacks reflect these M morphisms, so that in that sense these morphisms are stable on a pullback. That's going to be the essential construction. And I mean, what we saw earlier, like the regular monomorphisms, the edge reflecting ones, and simple graphs would be an example of such a class. Right, and the notation in the diagrams would be just sort of tail arrow just to emphasize, this will always be in the class M. And the other thing we will need will be the idea of an M initial object. So it's essentially mimicking the empty graph, the empty configuration. Only sort of technical complication is that you want this unique arrow that should exist from this object to any other to be in the class M. And I mean, that's again like one of these things, the list of axioms you need to check. All right, but now we are already immediately in the situation. So the actual calculus of conditions comes directly if you have a category such as state system of monics. So and a condition that's going to be conditions on morphisms. So first of all, we define something abstractly recursively, namely true is so always a condition is centered at an object X. So true on X is a condition, and then the nesting begins at there exists a morphism from X such that something holds over its codomain. That's sort of the first step of the nesting, and you're permitted nesting at, I mean, we can then continue the nesting if you wish. And we have we have a negation on conditions as well as conjunction. So from this you can build nice expressions. And of course, this is very useless if you don't have a notion of satisfiability. So a condition is satisfied, so the condition on object X is satisfied by a morphism from X, and here always it'll be M morphisms. Any morphism satisfies true, and then this interesting one is a condition that exists in F such that something over Y is satisfied if you find a morphism that composed with F gives H, and then this morphism should satisfy this condition too. So that's the second bit, and then you have a bit of logic here. So H does satisfy not CX if it doesn't satisfy CX, and so on. And then of course the junction. Okay, so that's calculus, and I mean it's useful because so far it's a bit abstract. Why on earth would we? I mean, it seems a bit indirect to give conditions on morphisms, and the trick here is that if you want to say something on objects, you say something about the morphism. I mean, each object has attached to it, it's this unique morphism from the M initial object. And now you can say, for example, and you basically say an object satisfies a condition over the initial object if if its unique morphism from empty satisfies it. And so you can say, for example, there does not exist two vertices such that on these two vertices there, and here actually I drew it parallel, that there are parallel edges. And that would be our simplicity constraint. But you could also say stuff like for all, and for all it just not exists such that not the condition, for all vertices with a loop, there also exists an outpointing edge, and so on and so forth. I mean, it's a very nice expressive language. Once you've seen it once, it's kind of makes sense, but okay. Anyways, good maybe to have the slide. Okay, and right, and one of the interesting bits is that it is first order logic. So I mean, there's many ways of expressing the same constraint, and so you have this concept of one condition is equivalent to another, that whenever one is satisfied, the other is satisfied. And I'll mention this again briefly in the end, but Barbara König and colleagues had some nice idea of using this, basically saying also the weaker notion, a condition is subsumed by another one if whenever the smaller condition is satisfied, the other one is also satisfied. And this way you can even formulate a categorical structure on these conditions. And I'll maybe mention this in the end. But okay, so for the moment, just to keep in mind, there's, nothing is for free. Of course, there's this problem of Pearl division. Okay, and now to do anything meaningful with these conditions in the context of rewriting, we will need two constructions. And one of them is called shift. But the idea of shift is that if you're on a certain object X and you have a condition over it, and you are using that condition, for example, on the input of a rule to test matches, then sometimes you need to extend the context of the rule, of the condition into a larger context. And then you want to have a condition, which is called shift, along this morphism of the condition that is always satisfied. So this morphism G always satisfies this condition whenever the composite satisfies the original one. So that's some construction we need. And here already, the question is what axioms. I mean, here it starts to really carry axioms. So far, we only use stable system harmonics, but I mean, now we are really touching on things we need to construct this. So, and this is, I don't know. I still find it a surprisingly complicated construction. So, shift of true is just true, but shift of a nested condition is not just a single contribution of a similar kind exists something, but it's an entire family of conditions. And so how does it work? So here is our morphism we want to shift against. Here's one of those that exists in A such that over A holds something else. So you first form a push out, and then you get one condition here. So there exists a Y into P such that the shift of this. And then you have to take all possible extensions of this overlap between A and Y, push out, and then you get, and you always get a condition of the shape that exists this R such that shift of CAS. So it's like, again, recursive even. Now, unfortunately, that's one of the roadblocks in working with this, that also in implementing algorithms, that the shift is unfortunately quite nasty. But it's guaranteed to exist and have the good properties as long as you're in an MRT category, it turns out. So that's good news. And then, I mean, there's a bit of logic here. Shift of not the condition is not of the shift of the condition, so on. Okay, and I just wanted to illustrate what this means in practice before getting any further details. So, I mean, let's consider a simple toy example. So here we have a shift from just an edge into an edge and a square. So that's our larger context. And the condition says over this edge should not sit a triangle. Well, I mean, one way in this context you have to check is that over this edge here does not sit directly a triangle. Well, okay, and then you have the square. But the problem is that then, I mean, in general, you start to get contributions like here where, for example, this edge could sit below the square and it should not have a triangle with that. I mean, here it's completely symmetric with any vertex of that square. So you see, that makes the calculus quite complex, and why it's non-trivial to speak about sequences of rewrites, because, I mean, you will see in each step there is some shifting involved, and so it's quite unclear why this should be in any ways compositional, right? So we need a good theory about to prove this abstractly. And by the way, then this is in the end effect here in this simple example. There is just two contributions. These are the two conditions you gain.
As you pointed out, one can translate all these nested conditions into first order logic.
Yes.
Which may be very useful for people who would just want to, who don't want to see the mechanics down there in the machine, and first order logic, of course, is 100%. More commonly known than this morphism based.
Kind of working with one formula position the chip just push out.
Okay, yeah, but then the instantiation is more complex. I mean, I don't know. I mean, I have the feeling that at the end of the day, you get a lot of trade-offs here, and then the algorithm is still
okay.
Yeah. Okay. So
there is a functional conflict between that part.
Yeah, it's something like that.
But it stays in.
Exactly. Right. Right. So some properties of the shift, which is interesting. So if you shift along an isomorphism, nothing happens. And I mean, I guess with Fernando's comment, it's clear without along isomorphism. But there's this other thing that if you shift, so the unit for shift are actually any isomorphisms in that sense. And then if you shift along a sequence of morphisms, it is indeed the case, I mean, this is in that sense composition that you just shift along the composite of those morphisms. So there's a certain kind of nice structure to these shifts. Right. And now, so this is, and I mean, conceptually, this is sort of the kind of technology we need to reason about matches and then, extending context and so on later on in the writing smartness. But now what about the actual, I mean, the task was to somehow reason about, so what's the writing step as a condition, say in a moment, but I mean, how do you reason about sequences in such a way that you can synthesize composite rules with their consistent conditions? And for this, of course, we need a little bit of terminology. So I'm just mentioning this here. So the usual universal constructions, push out, pullback, I guess they're known, but maybe not so well known is final pullback complement. So just a quick recap. Final pullback complement is a special kind of pullback square, such that whenever you extend in this fashion, then you find a unique morphism that mediates and such that both squares are pullback. So I mean, and you need that for Sesky-Bouchard writing, which is why I mentioned this here. There's quite a different construction from Bouchard and pullback in a sense, because its universal property doesn't at first sight look at anything similar to just a simple span or cospan type of argument. But okay, modulo that, we can now write down what means an individual direct derivation with conditions, of course. So the two variants we were interested in that work were double push out, where this is a push out square and this is also push out, or Sesky push out, where this is a final pullback complement and a push out. And then the only thing that is extra, if you want to have a rule with conditions at this stage, is you just put a condition over the input object and you ask that the match satisfies it. Generically, that's the rule. And then you could ask, oh, this is very asymmetric. Why don't you put a condition over O? And we'll get to that. But that's sort of the, I would say that's I mean, this sort of idea has been around at least, I think, since the 80s. Maybe not for Sesky push-out writing so much, but for double push-out. And now we need a bit of technology. So it turns out the compositionality of this is a complicated bit. So we need something called multisums. And the idea is essentially, I mean, in the adhesive category, it would be just jointly surjective monic spans, cospans. But I mean, generically in simple graphs, for example, it's quite a bit more complex. But the idea is that you have a family of M morphisms such that if you give me any cospan, that I can uniquely factor it through an element in this family. And here we present it in such a way that there's always one cospan that you find here. I mean, generically you'd have family set of cospan that are equivalent, but let's put it like this. Then it's okay. And so, as I said, in an adhesive category, it's always the case that you can model this as a cospan that you get by pushing out monic overlaps, and then you pick one per cospan isoclass. And that's your multisum. Okay, and now comes a really strange observation. Something we only found, I mean, in this paper with Russ and Jean, we favor a little bit this double categorical style of presenting direct derivation, simply because then you can reason about double push-out and Sesky push-out in one go. So it's a bit more efficient. And the weird property that we need for compositional writing and for, you know, this reasoning about conditions is that you can split a direct derivation vertically in a certain way. So whenever you give me a rule and a co-match, then there's a family, possibly empty, of direct derivations like of this shape, and such that this is universal in a sense. If you have any direct derivation of this shape, where the co-match is factorized, you can split it horizontally. Well, it turns out that this has a clear mathematical meaning, because what we want here is that this family is, if you look closely, this means that if this family is empty, then this condition doesn't hold, and doesn't trigger. But if it's non-empty, then any two elements in the family are actually isomorphic. But I mean, here we want to fix it in such a way that we pick exactly one element in that family, meaning that this is a so-called obfoliation structure. And I mean, you know that in double push-out writing, I mean, if you give me any match or co-match and a rule, then the push-out complement might exist or not. But if it exists, it's unique after isomorphism. And then I pick one representative. And that's how this sort of construction should work. Which means that for double push-out rewriting, there's a symmetric thing for if you start from matches. Indeed, now this is exactly the same picture. But for Sesky push-out rewriting, you actually find something stronger, that for every match you have exactly one such derivation. I mean, you have one, and you have exactly one up to isomorphism, and that is simply because you have a sort of final pullback complement under the correct requirements on your category always exist along these M morphisms, and then you can just push out. So I mean, this exists uniquely up to universal iso. So these are the two things. We need to be able to split in some shape derivations vertically. Okay, and and I mean, in this paper, it's a 51-page paper, but it turns out some of the most complicated proofs can be summarized quite nicely in this calculus. And the one thing we need for a certain construction I will introduce next to be compatible, when we have such a direct derivation where the co-match splits, you can use this obfoliation structure to split. And then you could go again in the other direction. You now split it from this side. And what you'll find by the universal properties is that here you will get an isomorphism. So up to isomorphism again, sort of splitting in this direction and in this direction, you do a null round, you have split the whole thing vertically nonetheless. So it's, and it has a direction, it has to go from here to here because in this direction is a weaker property in general. I mean, unless for VP opens. Okay, and now this is exactly now, funnily, the step where you get a very traditional construction from this calculus of conditions, but also for sensitive push out. So there's this idea that you want to have a construction that, and here now comes the point, why did you have this asymmetric thing just having conditional input? Well, if you want to say something about the output that the co-match should satisfy, there's a construction called transport, which provides you some condition over the input that whenever you have the match satisfying condition, the co-match will satisfy this condition here. That was very well known for double push-out writing and didn't exist until this paper for Sesky. But you see here now, it's very simple. The only, I mean, transport is nothing but performing exactly this obfoliation operation. So, and then there are some properties you say for the true, you always transmit this as true. Actually, if there doesn't exist this obfoliation element, then you set it to false because that can happen. And then you have like some little logic here about not of trans of not is not trans and so on. So that's very interesting. And so this already is then the explanation for this construction, for the existence. And now the final piece is, so transporting along something like an identity or actually span of isos is again a trivial operation. And then transport of, I mean, if you compose spans and the direct derivations on it, you can also compose the transes. The only thing is, I mean, this goes after this. So, I mean, the linearization is not quite nice, but okay. Anyways, and then the final piece is that you can check that there's funny compatibility. If you have a direct derivation and a condition here, you can either transport here and then shift, or you can shift and then transport. So that's a compatibility that these things satisfied. And all of that holds as long as you're in an adhesive category, which has this M initial object and so on. So that's actually the mathematical theory of what you can do with shift and trans. Now, sorry, I have maybe a few minutes now.
Yeah, a few.
Okay.
Leave also a 50-minute coffee break.
Yeah, exactly. Yeah. So now finally, we have all the machinery. I mean, evidently the bits are, but I mean, it's this idea of modularizing all the pieces of the theory so that later you can state the main theorems in a clean fashion. I mean, whether or not that's a good idea, I don't know. But for any of these situations now, we have now here a sequence of direct derivations, each with their own conditions. And now we'll produce ourselves a composite rule with a condition that emulates in such a way that when the sequence is possible, the one-step derivation along the composite rule is possible. And again, like if you know double push-out writing, that is the double push-out writing version. So first you take this multi-sum element to characterize the co-span. Then you go in this direction, and in this direction with these lifts, you split vertically. And now the thing is that you use shift and trans and the shift of this condition here. And this together will give you a condition on the overall input here. So in this situation, you produce a tracelet of length 2, so you could stop there. If you wanted to actually compute a composite, you can also do that. You just, compose horizontally these direct derivations. And that's the basic operation of this calculus. So basically, you have a means of producing logically and causally consistent rule composite or tracelet of length 2 with the right application condition. So this is already good because it was a sort of composing 2 steps into a box, which then just does the whole operation in one go. But sort of the main point of this is that we can now check whether our formalism is indeed consistent when you start looking at sequences. Because the idea, of course, is to do concurrency theory based on local church Russell and stuff like that. So we better make sure it survives like looking at sequences. So now we take 2 rules. We take a multi-sum element to compose and then these lifts to compose them. And of course, this we produce again by shift and trans and shift. Now we take a third rule, we compose it. We now simply, in this direction, we live with the ovulation, and here we do it twice. And that gives us a 3-step sequence. And now it turns out with all of this stuff we showed, we can, here we just take multisum. And here we now have the splitting of the composite of these guys. So again, I can lift, and similarly in this direction. And finally, here I can just see that this actually, for this to be in this sense associative, this would have to be a multisum element. But that is something you can show that in this configuration, this will then always be a multisum element if the underlying category is MRTs and so on. And finally, the funniest part of the proof is that the piece that is extra for conditions is almost for free, because now you do a funny diagram chase. So originally we had here a condition, and its contribution to the overall condition was you shift here and you go all the way here, and that's one condition. In the new contribution, it goes here, and then, I mean, you have a free choice. Sorry, it goes here, and then down here and here. And in the middle, you have exactly one such little plaquettes where you have to go around or like this. And that's the only piece you need to prove this sort of associativity. And then similarly for all of the others, if you shift along the same, an arrow which composes to the same, that's the same contribution and so on. So, I mean, by a little diagram chasing, you can show that this is actually then fully associative, and you do not need any new conditions over being MRTs. So that was a good story, I think. Okay, and so just final comment quickly. So there's one very interesting piece of work by Barbara König and colleagues, which is on these conditional reactive systems, where they thought about a little bit what happens if you consider this category of conditions over a given object of a host category, because then it turns out that this shift is has some is actually functor with a left and a right unjoined of some interesting structure. And I mean, if anybody of you ever thought about this in any detail, I would be quite interested. Have a chat. And then there's this other piece where you start looking at constraint preserving conditions, also a concept well known from the literature. And again, morally speaking, since whether you're a Sesqui or double pusher doesn't really matter as far as it comes to the calculus on the matches, so on the shifts and so on, this can carry over to Sesqui as well. And so it turns out for constraint preserving conditions, there's a nice compression possible. You can give a composition concurrency theorem, optimize it for reusing the constraint preserving condition as much as possible. And in that way, you get a tractable way of computing, with chemical rules and biochemical rules. So if you're interested in that, it's also, I bet that was one of the last year ICGT papers. So yeah, and with this, I better close.
Okay, thanks, Nick. Some quick questions, perhaps, if there are any.
You said intuitive. There's an interpretation is more intuitive that you can say that conditions are conditions on the and the idea is the following: you work in first order logic, you have a formula with 3 elements, 3 variables, then you say that this formula is satisfied by a given model if you have a substitution of the 3 variables into the model.
I mean,
typically you define it as you have the formula and the substitution and you claim satisfaction. So if you see the morphism as a substitution in the formula, then you can claim that the condition is a condition over a model, and even that substitution, that morphism substitution, then
yeah, I mean, the first order logic, of course, is logic on graphs, and it's a logic on morphisms, essentially.
Yeah, then it would become a logic on graphs.
Yeah. Okay, yeah, thanks for that comment. Anything else, right? Oh, can we have more coffee? No. It's like, okay, thanks again.
I don't